in this part over here, state that there are two types of electric charge. Obviously, we have our positive charge and our negative charge. The positive charge basically comes from the protons, and the basic unit charge, the fundamental charge, is 1.6 times 10 to the negative 19 coulombs. Charge is measured in coulombs, and this is a positive charge, and our electrons are the basis of our negative charge, and there it's the same magnitude of charge, but just the different sign. It's negative. We've decided to call electrons negative and protons positive, and we have the opposites attract, and like repel. So with your charge, we have both an attraction and a repulsion, where in gravitation we just had our attraction. So for this over here, we can apply what we call a law of conservation of charge, which means that charge does not get destroyed, it just gets distributed in different ways. You don't destroy charge, you just change it into one form or the other. So here it is over here. Charge is always conserved in any action. The distribution of the charge is changed. That's your law of conservation of charge, which is given over here. Now, this idea of conductors and insulators, I think you have a good idea of what those are. Conductors allow the flow of charge, where insulators don't allow the flow of charge. So in insulators, charge cannot flow freely. Coulomb's law is given to us by this formula over here, which is very similar in style to Newton's law of gravitation, universal law of gravitation, where the force is proportional. Your force is proportional to the product of the charges, and the force is inversely proportional to the square of the distance between the charge. And we combine that into one formula with a law, with our constant for this formula is given by K. I think it's about 9 times 10 to the 9. You can get that value. The value of this is around about that value. As you can see, it's a much larger numerical value than your G, your universal gravitation constant. Now, just as in this over here, we get our gravitational field strength, we also get our electric field strength, which is our force per unit charge again. So it works exactly the same way. It's a force per unit charge. So if I take my K Q1 Q2 over R squared, and let's say I'm looking at the force caused by the force per unit charge caused by Q1, then I'm going to divide it by Q2, right? As before, so I divide both by Q2, and we get E is equal to KQ over R squared. In this case, it would be Q1. So this is the electric field strength due to a point charge. Point charge. And again, we need to be able to add up our separate electric field strength if we have more than one charge acting on another charge. So for instance, again, if I have say Q1, which is positive, and Q2, which is negative, and I have Q3, which is positive. Now we would obviously have an electric field strength due to Q1 acting on Q3 in this direction, because it's repulsion. Alright, they are repelling each other. So this would be the electric field strength on Q3 due to Q1. And then we would have our, yes, we would be dividing that by Q3. and this one would, so that would be E is equal to KQ1 over this distance between them, R1 squared. And then we'd also have a force, but this would be an attractive force. So this would be a force in that direction, so we'd have an electric field strength there, E2, acting in that direction, and that would be due to Q2. So that would be E is equal to KQ2 over R2 squared, the distance between Q3 and Q2. And the combined electric field strength would be the addition of these vectors. So we would add those two vectors together and we'd get our combined electric field strength due to 1 and 2 in that direction, like that. So you need to be able to add these up, you need to be able to work them out and add up those vectors. Now finally we also have this formula over here, which is just another way of writing this formula over here, except we have K is equal to 1 over 4 pi this epsilon 0. Now this is, if I've got this right, is the permittivity of free space. Now the reason for this is that this K value is given for free space, for air and for a vacuum. But if we were dealing with, and sometimes with electric fields, we are working in things like oil, for instance, and this K value will actually change, and this E0 will can actually have different values for the material that we're dealing with. So if you are given your permittivity, then you may have to change that value. Generally we always use this formula over here unless we are dealing with another material where this is actually changing. This E0 is actually changing. But 1 over 4 pi E0 is equal to K. Now the electric field strength due to parallel plates, if I have two parallel plates and I have a potential difference across them, something like this, say that is V, and the distance between them is D, the electric field strength for this situation is given by the formula E is equal to V over D. Alright, now that is a formula that you need to remember. And the electric field strength between parallel plates is constant between the plates. So you'd actually draw them by electric field lines that are parallel to each other and equally spaced. And they also hit the plates at 90 degrees. It's only at the end do we get a bending like that. But this is your electric field strength due to parallel plates. This formula over here, E is equal to KQ over R squared, is due to a point charge. That's electric field strength due to a point charge. Now, you need to be able to draw diagrams of this, and these diagrams have to be well drawn. So I will just show you what I mean by this. Here we have different diagrams of the electric field between different charged spheres. Now, the arrow on the electric field is due to the direction that a positive charge would move. So we can see here that if we put a positive charge near a positive charge, the positive charge would want to move away. So it's the force, the arrow is the direction of the force of a positive charge. So all of these, we would have a positive charge over there, so Q plus. What would a positive charge do? Now, whenever an electric field meets a conductor, it always meets it at 90 degrees. So whenever it meets the conductor, it's always at 90 degrees. The density of the electric field lines gives an indication of the electric field strength. So we would expect for this over here that your electric field strength, for instance, over there at A would be stronger than at B because the electric field lines are more separated. They're not as dense, closely spaced. here you can see here that this is a uniform electric field because they are parallel and they're evenly spaced. So with drawing these diagrams, you need to use, if possible, a ruler. They need to be accurately done, and you need to do them with care, and these electric field lines should never cross over. So if you asked to draw an electric field perhaps around a sphere like this, a positive sphere, you can't have something like this where we know that they'll be going away, that they cross over or whatever. Your electric field lines never cross over each other. And they obviously need to be drawn with a certain amount of precision. One final thing, if you look at this diagram over here, you'll see that your electric field lines are more closely spaced over here, and that's because charge congregates in areas where there's the greatest curvature. So the greatest curvature leads to the greatest buildup of electric charge. And I don't know if you've ever seen on your lightning protectors, you'll see that they're often very spiky. They're trying to create a lot of curvature because that builds up a lot of electric charge, and that leads to a place where the lightning will likely strike or build up enough charge to strike. So you can see here in this one over here, you get a higher curvature, and therefore you get more positive charge there, and therefore your electric field lines are closer spaced than, for instance, over here on the other side.